Applications of maxima and minima. Finding extreme values has many applications in life. The business owner who desires to minimize cost while maximizing profits. The architect charged with maximizing an enclosed area with the least amount of materials. And in the world of calculus, we search for the optimal or best value for these problems. These problems consist of the following components. Unknowns we're asked to determine. An objective function. This is the function that must be optimized, where we ask for the greatest or least quantity. Constraints on unknowns, often represented as equations that serve to relate the variables. And then we need to take the objective function and simply rewrite it in terms of a single independent variable. Once this is done, a solution is determined by applying the first derivative test. But the last step is to verify that the solution was the optimal solution. That is, if a maximum value was requested, did the first derivative test yield a maximum or a minimum value? Let us begin. A manufacturer produces tuxedos to be sold in batches up to 300. How many tuxedos should be produced to minimize the average cost? So notice a cost equation is provided. 0.4x squared plus 20x plus 3,240. First question we ask ourselves, what is to be optimized? Well, we go to words, greatest, least, maximize, minimize, and we see it's the average cost. What's the unknown? Well, that'd be the number of tuxedos, x. What is the objective function? Well, it would be the average cost function. This is determined by finding the quotient of the cost function in x. So the units would be cost dollars per each tuxedo. The constraints in this case is an interval. We will sell in batches up to 300. So we're looking at an interval from 0 to 300 inclusive of 300. The objective function then needs to be written in terms of a single variable. So since the objective function is the quotient of the cost in x, we rewrite it as the cost function divided by x. And then take a moment to divide each term by x to get the friendlier version of the average cost function. 0.4x plus 20 plus 3,240 over x. To find the solution, we will take the first derivative of this function. So we've chosen to rewrite our function in a friendlier term to avoid a messy quotient rule. Well, let's determine the solution. We take our average cost function, we differentiate. Derivative of 0.4x is 0.4, derivative of the constant 20 is 0, and 3,240 times x to the negative 1, its derivative, swing the negative 1 out front, multiply by 3,240, take x to the negative 1 minus 1, and we have our first derivative. Take the first derivative and set it equal to 0. So we have 0.4 minus 3,240 over x squared set equal to 0. Now the goal is to solve for x or see where this first derivative is undefined. We find a common denominator and we pause long enough to realize the first derivative is undefined at x equals 0. And I'm looking at this denominator right here. But remember, our interval was 0 to 300 inclusive of 300. In other words, 0 is not in the domain of our function. So as we proceed to solve, our focus becomes on the numerator solely. 0.4 times x squared minus 8100. And we solve by taking x squared minus 8100 equal to 0. Add 8100 to the other side, and take the square root of both sides. But again, remember our domain. 0 to 300, inclusive of 300. The only critical point of relevance is x equals 90. This is a stationary point because this is where the first derivative is equal to 0. So the solution is x equals 90. We want to verify, though, that this solution yields a minimum average cost. So we take a value of x less than 90, say 80, evaluate it in the first derivative, and find the first derivative evaluated at 80 is negative. Left of 90, the function is decreasing. We take a value of x that is greater than 90, say x equals 100, evaluate it in the first derivative, and we find the first derivative evaluated at 100 is positive. Right of x equals 90, the function's increasing. It looks like we have indeed found a relative minimum. Now, if we take x equals 90 and substitute it into the original function, we call that was the average cost function, and evaluate, we can interpret our response. The average cost when 90 tuxedos are produced is $92. 92 is the average cost function evaluated at 90. And this is the smallest average cost per tuxedo. We can verify graphically by sketching the average cost function on the domain 0 to 300, and we can see the absolute minimum very clearly. The point that serves as a location of the absolute minimum and the absolute minimum is 90, 92. Let's look at a second example. A rancher would like to enclose two adjacent rectangular pens of the same dimension to produce the greatest possible area. She has 400 feet of fencing. Determine the length and the width of each of the pens. We begin by asking, what are we trying to optimize? Go to words such as least and greatest, and we find we're looking for the greatest possible area. We're trying to optimize the area of the pens. Quick sketch of two pens that are adjacent, side by side, and the same dimensions shows that if the unknowns serve as a x variable for the width and a y variable for the length, we very quickly arrive at an objective function, which is the area of each pen is x times y, or length times width. There are two pens. Therefore, the objective function, what we're trying to maximize, is 2xy. But this function is in terms of two variables, and we would like to write it in terms of one independent variable. So we glance through the constraints, which are garnered from this sentence that reads, she has 400 feet of fencing. And if you notice, this enclosure has four widths of length x and three lengths of length y. So 4x plus 3y equals 400. The purpose of writing the constraints is so we can solve for one variable in terms of another, so we can write our objective function just in terms of either x or y. Arbitrarily, we solve for y. Y equals 400 minus 4x divided by 3, which leads us to writing our objective function in terms of one independent variable, x. Area in terms of x is 2x times, well, y, which is rewritten as 400 minus 4x divided by 3. If we wanted to find the solution with the first derivative test, we would differentiate in our next step. So we'll take a moment to rewrite our function so that it's more amenable to differentiation. This first version would require the product rule. But if I distribute the x through the parentheses and factor out the 1/3, and rewrite the function as 2/3 times quantity, 400x minus 4x squared, I can now differentiate each term, thus avoiding the product rule. So in determining my solution, I will choose the version 2/3 times 400x minus 4x squared. I'll differentiate 2/3 times 400 minus 8x. And then we set the derivative equal to 0. It's defined everywhere, so now we want to solve. Set the equation equal to 0. Divide both sides by 2/3. Isolate x, and we get 400 divided by 8. X is 50. We pause and say, what was the question requiring of us? It required that we found the length and the width of each of the pens. Well, we found the width. Now we find the length by substituting 50 into the equation y equals 400 minus 4x divided by 3. We find y to be roughly 66 2/3, which means the solution is that each pen is of dimensions 50 by 66 2/3. If we wanted to verify, we would take a value of x that is less than 50, like 40, substitute it into the first derivative, and we find that first derivative evaluated at 40 is positive. Left of 50, the function is increasing. Right of 50, we choose a value of x, say 60, and we evaluate the first derivative at 60. Find the first derivative is negative. Right of 50, the function is decreasing. It looks like we have found a relative maximum. This coincides with the fact that we were looking for a greatest possible area. We would not want it to have found a relative minimum. We would like to have found a relative maximum. This enables us to answer the question, the maximum area of each pen is 3,333.3 square feet. More than enough room for a large group or small pony. Thank you.